Hello! In this video, we'll compare two popular machine learning frameworks, JAX and PyTorch. We'll implement the exact same use case in both frameworks to see how they differ. The advantages and disadvantages of each framework depend greatly on your specific use case and even the hardware you're using. Instead of making definitive claims about performance, we'll focus on the overall user experience and key differences between these frameworks. One important difference to note is that JAX is often run on Google Cloud TPUs, or tensor processing units, while PyTorch is traditionally used with NVIDIA GPUs. Both frameworks work well on any hardware, but you'll get the most bang for your buck using TPUs with JAX and GPUs with PyTorch. We'll explore both hardware options in our comparison today. For our evaluation, we'll use Google Colab connected to powerful Google Cloud VMs rather than the default Colab runtime. This setup will give us access to serious hardware to properly test both frameworks. We won't necessarily need this for our simple testing, but it'll provide you with a great foundation for more rigorously testing your specific use case. Let's start with setting up our GPU environment for PyTorch. We'll use Google Cloud documentation to select a configuration with NVIDIA L4 GPUs. Specifically, we're looking for a G2 instance with 8 GPUs, the largest L4 machine available. This costs about $8 per hour at on-demand pricing and provides 100 CPUs, 400 gigabytes of memory, and 8 GPUs. This is more than we need, but it will demonstrate how PyTorch performs on high-end hardware. Now let's create a compute engine instance with these specifications. We'll select the GPU machines, choose L4, and pick the 8 GPU configuration. We'll keep most settings as default, but we need to allow SSH traffic so we can connect our Colab environment to this VM. We'll add a Colab network tag to help with this. Let's create this instance in US Central. While our GPU instance is being created, let's set up our TPU configuration for JAX. Although both frameworks can technically run on any accelerator, JAX typically gives better performance per dollar on TPUs. The TPU V5e chips cost about $1.20 per hour each, so 8 chips would cost roughly the same as our L4 VM. Conveniently, we can run all 8 chips on a single VM. Let's create a TPU machine with 8 V5e chips, also in US Central, to match our GPU instance. We'll use Ubuntu for the operating system and select V5 Lite Pod 8 to specify we want an 8-chip V5e instance. As with our GPU instance, we'll add the Colab network tag to allow SSH connections. Let's create this instance now. Our GPU instance is now running. Let's SSH into it to check if we need to install any drivers. As expected for a new VM, we don't have NVIDIA drivers installed yet. Let's check the Cloud GPU documentation for installation instructions and follow the Linux pattern. This installation comes from an open source repository, and we confirm we have Python 3 on our system, which is required. The installation warns us that it might take some time and could restart the VM. After receiving a warning about a system reboot, let's manually stop and restart the VM to be safe. After rebooting, let's SSH back into the VM and check if the driver installed successfully. We need to run the installation script again to complete the process. Now the output suggests we have successfully installed the driver, and running the NVIDIA SMI command shows our 8 L4 GPUs, confirming the installation worked. Let's check on our TPU instance. It seems there wasn't enough capacity in our selected zone. Let's try again in US Central. Success. Now we can SSH into this VM with TPU V5e chips. Installing JAX with TPU capabilities is much more straightforward than the NVIDIA driver installation. We just need to run a pip install command with the optional TPU dependencies. A quick test shows that our TPU devices are recognized, so we're all set up. Now we have two similarly priced environments, PyTorch running on L4 GPUs and JAX running on V5e TPUs. This gives us an excellent foundation for our comparison. Based on our setup experience, we can already note our first comparison point, installation difficulty. For PyTorch with GPUs, the installation is moderately difficult. Managing CUDA versions and NVIDIA drivers can be quite challenging, especially if you haven't done it before. In contrast, JAX installation with TPUs is much simpler. So in terms of pure installation experience, JAX has an advantage. Now let's connect our Colab runtime to these backend compute engine instances. We'll use the MNIST dataset to build and compare machine learning models in both frameworks. We'll start with the GPU side for PyTorch. To connect to our GPUs, we need to choose Connect to a local runtime in Colab and provide a backend URL. While Colab's built-in runtimes offer a single L4 GPU or V5e chip, our setup gives us access to multiple accelerators, allowing us to explore parallelization capabilities. First, we need to configure networking to expose our VMs. Let's create a firewall rule to open port 8888 for SSH connections. We'll call this rule Allow Remote Colab, target our Colab tag, and allow TCP connections on port 8888 from any IP address. Now let's set up a notebook environment on our GPU VM. We'll SSH into the VM and install JupyterLab and the notebook package using pip. Since this is an externally managed Python environment, it's good practice to create a virtual environment first. After setting up the virtual environment and installing our dependencies, we'll start a Jupyter Notebook server on port 8888, making sure it's accessible from any IP address. We copy the token from the output and access the notebook in our browser. Note that we're using an unsecured HTTP connection, which isn't recommended for sensitive networks. In a production environment, you'd want to set up HTTPS. We can create a new notebook with a Python 3 kernel and run the NVIDIA SMI command to confirm our GPUs are accessible. Great, now let's do the same for our TPU instance. After setting up a similar notebook environment on our TPU VM, we verify that our JAX installation can access the TPU chips. Excellent. We now have both environments ready for our comparison. Now let's start writing some code. We'll begin with PyTorch on our GPU instance. First, we need to install PyTorch and related libraries. While that's installing, let's learn a bit about the MNIST dataset we'll be using. MNIST is a classic dataset from Jan LeCun and colleagues, containing thousands of handwritten digits 0 through 9. Each image is 28 by 28 pixels in grayscale. Our task is to train a machine learning model to recognize which digit is represented in each image. This is a supervised learning problem since we have labeled data for training. Oh, we've encountered a storage space error. It seems our default 10 gigabytes boot disk is too small. Let's increase it to 64 gigabytes in real time through the Google Cloud console. After expanding the partition and file system, we retry our installations, which now proceed without issues. Let's import our required PyTorch modules and load the MNIST training and validation data using the Torch Vision library. This conveniently handles downloading the dataset. Let's explore the data. The first training example is an image of the digit 5. The images are initially in PIL or Python Imaging Library format with pixel values from 0 to 255. We'll convert them to PyTorch tensors with values normalized between 0 to 1, which works better for training neural networks. By default, these tensors are stored in CPU memory. To take advantage of our GPUs, we move them to CUDA memory using the .CUDA method. We can also convert back to image format for visualization if needed. Now let's properly prepare our data for training. We'll set the transform property of our datasets to convert images to tensors. We'll use a batch size of 32 and create data loaders that shuffle the training data. Our neural network will need flattened inputs, so we note that our 1 by 28 by 28 images have 784 pixels total. Let's define our neural network architecture. We'll create a flattening layer to convert 2D images to 1D vectors, an input layer with 512 neurons, and ReLU activation, a hidden layer with 512 neurons and ReLU activation, and an output layer with 10 neurons, one for each digit. We compile this model and move it to our GPU using the CUDA method. For training, we need a loss function and an optimizer. For a classification problem like this, we'll use cross-entropy loss and the atom optimizer. Let's check our GPU utilization. Interestingly, we're only using the first GPU out of our 8, and even that one is barely utilized. This is because our model is so small that it doesn't need much memory or computation power. To track our model's performance, we'll define a function to calculate accuracy. Now let's create our training loop function that calculates loss, performs backpropagation, updates weights, and tracks both loss and accuracy. We'll also define a validation function to evaluate performance on unseen data. With everything set up, let's run our training loop for 5 epochs and time how long it takes. It completes in about 52 seconds. We can test our trained model by giving it an example input. It correctly predicts our test image as the digit 5. Success. Now let's switch to our TPU instance and implement the same model using JAX. One immediate difference we notice is that JAX doesn't have built-in dataset loading functionality like PyTorch. Instead, we'll use TensorFlow's dataset loader, which we need to install first. This highlights a key difference. PyTorch provides almost everything you need out of the box with many utilities and abstractions, while JAX takes a more minimalist approach. Whether this is an advantage or disadvantage depends on your preferences. If you want a comprehensive, integrated toolkit, PyTorch may be preferable. If you prefer a leaner, more flexible foundation, JAX might be better. After installing TensorFlow, we import the necessary libraries and load the MNIST dataset using TensorFlow's dataset loader. Let's examine the data structure. We'll take the first image and label and convert the tensor to a NumPy array for visualization. This brings us to another observation. For data loading and exploration, PyTorch provides native functionality while JAX typically relies on external libraries like matplotlib and NumPy for visualization. If you prefer working within a single ecosystem, PyTorch may have an advantage here. Now we need to pre-process our data for JAX. We'll create a function to resize and normalize the images, similar to what we did with PyTorch. We'll use the same batch size of 32 and set up prefetching for efficient data loading. Let's initialize our neural network. Just like in our PyTorch example, we'll use 512 neurons in our hidden layer. However, you'll immediately notice a different approach to random number generation in JAX. This reflects a fundamental philosophical difference between the two frameworks. PyTorch follows an objective-oriented programming style with lots of hidden state management. Meanwhile, JAX uses pure functional programming where state is explicitly managed and functions are pure. Their output depends only on their inputs. This difference becomes apparent when generating random numbers. JAX's approach is quite different from PyTorch or even NumPy, despite JAX syntactically resembling NumPy in many ways. If you're doing lower-level machine learning work, JAX's approach can provide more precise control and transparency. There's also a difference in abstraction levels. PyTorch generally provides higher-level abstractions, while JAX exposes more lower-level details. If you want fine-grained control and visibility into what's happening, JAX often has an advantage. As we continue initializing our neural network parameters in JAX, notice how we're explicitly defining many lower-level operations, like how we generate random numbers and initialize network parameters. Now let's define our forward pass function. We can use helper libraries in JAX, such as the NN library, which is part of JAX natively. To match our PyTorch example, we'll use ReLU activation instead of swish activation. Let's test our forward pass function to ensure it returns the expected shape. A 10-element vector of activations, one for each possible digit. Indeed, that's what we get. A cool feature of JAX is its vectorization capability. We can process an entire batch of images at once using the vmap function, which automatically vectorizes our operations. Another advantage of JAX is how it handles hardware acceleration. When we check our device, we see we're automatically using TPUs without explicit device management code. In PyTorch, we had to manually move tensors and models to the GPU using CUDA or to-device methods. JAX transparently takes advantage of the available hardware accelerators, making the code cleaner and more portable. Next, we implement our loss function, categorical cross entropy, just like in PyTorch. For updating gradients, we use JAX's grad function, which handles automatic differentiation. Another useful JAX function is value and grad, which returns both the loss value and the gradient in one call. For our training loop, we'll use a one-hot encoding utility from JAX and train for 5 epochs, just like in the PyTorch example. Notice that in JAX, we're explicitly passing the parameters as input and returning updated parameters as output. This is part of JAX's explicit state management approach with pure functions. Let's run our training loop and time it. The training takes about 3 minutes, which is notably slower than PyTorch's 52 seconds, despite having similar neural network architectures. However, there's a powerful optimization we haven't used yet in JAX, the just-in-time or JIT compiler. By simply adding the @JIT decorator to our update and accuracy functions, we can dramatically improve performance. After this change, our training time drops to just 13 seconds, much faster than before and now faster than PyTorch. This demonstrates a key advantage of JAX, its powerful compilation capabilities that can automatically optimize code for specific hardware. While you can squeeze out performance in PyTorch through various optimizations, JAX's JIT compiler provides significant speedups with minimal effort. In conclusion, both frameworks have their strengths. PyTorch offers a comprehensive, batteries included approach with many utilities, more intuitive, object oriented programming style, excellent documentation and large community support, and native support for common deep learning operations. JAX offers powerful compilation and optimization capabilities, a functional programming paradigm with explicit state management, excellent support for TPU hardware, more fine grained control for advanced users, and impressive performance with JIT compilation. The choice between PyTorch and JAX ultimately depends on your specific use case, programming style preference, and available hardware. PyTorch might be better for beginners and those who want a comprehensive toolkit, while JAX could be more preferable for researchers who need more control and performance optimization capabilities. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include the diagram file in the description as well. If you have any questions, please post them in the comment section and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.